This is Professor Rudy, and this video is about the discussion of how to use vectors and do some basic plotting in MATLAB. So what is a vector? Well, a vector in a software like MATLAB is basically a way of storing a bunch of different values in one variable. Now, there are some different ways to create vectors. The simplest way is to define a vector, so we could just do something simple like v equals, and then by using square brackets we can put whatever values we want in there. So if we want the values 3, 2, and 7, we can create a vector with these. Now here we've separated those numbers by commas. We can also separate them just by spaces, so I can do that same thing, 3, 2, 7, with just spaces. And whether we use commas or spaces, we end up with these values in a row. We can also see in our workspace here that we have the values of all three values stored in that one variable v. Now we could also do this, but rather than commas or spaces, using semicolons to separate these values. And if we do that within our square brackets, we end up with the same values, but this time listed in a column. This is called a column vector. And this is how you can define that with whatever values you want. Now sometimes you want to generate a vector using a large number of values that you don't want to type out by hand. So one simple example would be, what if you wanted the numbers from 1 to 10, but you didn't want to type them all out? And there, in MATLAB, there's an operator which is the colon. So if you use 1:10, what that will do is that'll create a vector that goes from 1 to 10 in increments of 1. So if I hit enter there, I get 1, 2, 3, 4, up to 10. Now this operator, we can do this from any range. What if we only wanted the numbers from 4 to 12 instead? And it'll go 4, 5, 6, up through 12. Now with this operator, if you just have the two arguments, one to the left and one to the right, it will just go from one to the next in increments of 1. But sometimes you don't want to use an increment of 1. We could also increment by any value. One thing we could do is increment by a half. So I could go from 0 by 0.5 up to 4. And if I do that, I get values 0, 0.5, 1, 1.5, and so on up until I hit that upper limit of 4. And that's how we can use the colon operator. Although it's not very common, you can also do a decreasing increment. So you could do a vector that goes from 10 by -1 down to 3, and that'll go 10, 9, 8 down to 3. So that's also something you can do, and it doesn't have to be 1 or a half. You can use any increment, and you just put that increment in the middle between those two values. Another function that you can use to generate a vector automatically is the linspace command. And if you remember, anytime we want to see what a command does, we can do help and then look at what MATLAB has for us. So what linspace does is it creates a linearly spaced vector, and it does this by, and let's just look at this second one here. We go from the first value to the second value, and we do that in n points. So we could do something like we did before. So if we wanted something to go from 1 to 10, we could do linspace 1, 10, and then 10 points. So from 1 to 10, 10 points, and then we'll get 1 through 10. But what's nice about the linspace command is you can give it any number of points you want. So you don't have to worry about figuring out what the increment is. If you know you want from 1 to 10, and maybe you just want 13 points, and it will decide what that increment needs to be and give you those 13 values. There's also another function that does a similar thing to linspace, and this one's called logspace. So the lin part for linspace was linear. And the difference here for logspace is that it's not going to do even linear increments, it's going to do logarithmic increments. So this is useful if you're doing things on a log scale. So how this works is, rather than from the first number to the second number, it's given in powers of 10. So it's 10 to this power to 10 to this power in endpoints. So if we wanted to do a simple example there, we could do log space from 1, so that would be 10 to the first, to 3, that would be 10 to the third, or 1,000. And if we do that just as 3 points, we'll get the 10, 100, 1,000. But what's nice about this is if we wanted to do that but get more values in between, we don't need to worry about that increment, because it'll fill that in there. So by going from 10 to 1,000 but get 5 points, we fill in those values in there, but on the logarithmic scale, not the linear scale. So once we have a vector, so let me go with a reasonably simple vector of 0 by a half to 4. So we have this vector 0, 1/2, 1, 1.5, and so on. Once we have that vector, what we can do is we can reference different parts of that vector. So if we do v of 1, so within parentheses we give it an index, and this will give us the first value in that vector, which was 0. So we could similarly do this for the second point and get that the second point was a half. Another thing you can do is maybe you don't know what it is, but if you want the last value in the vector, you can do v of end and say, what's the value at the end? And that's 4. Now, in addition to just passing a single value into parentheses, you can also send in a vector. So you could say v of, and you could explicitly say I want the second and the fourth, and I'm putting those in a square bracket because that's how we can create a vector. And if I do that, it'll give me the 1/2 and the 1.5, so the second and the fourth components. Now we can also do this combining with what we learned earlier and use the colon operator. So maybe I just want the 4th through the 6th value. So values 4, 5, 6. That's what that colon operator will create. And then that'll pick out those values for us. Another interesting thing you can do is if you wanted every other value in that vector, so let's say the odd components, we can do that by saying v of 1 by 2's to the end. So starting at 1, incrementing by 2, so that'll go 1, 3, 5, until we reach the end of that vector. So if we do that, we'll get the odd pieces, which in this case are the integer values. Now we can also do this in the even components if we just do the same thing but starting at the second value. So then we'll go 2, 4, 6 to the end, and if we do that, we'll get those even components of that vector. So now I'd like to go into some more detailed examples. So I'm actually going to create a script for this. At the very least, when you're starting a script, you at least want to put your name on it. It's also usually good to put the date and some idea of what the program's going to do. So this program will go through examples related to vectors and plotting. Also, at the start of a script, it's good practice to put clear all, clear the workspace, so you don't have variables from previous work entering in your code and messing things up. So we'll clear all there, and then what I'm going to do first is I'm going to define a time vector, which is going to be, I'll call it t, and I want that to go from 0 in increments of 0.01 seconds and go to 10 seconds. It's good practice when you define a variable like that. If you want units in your problem, to use what's called an inline comment. So we put that comment over to the right of the line, and that's telling us that that time is in seconds. Next, I want to calculate some functions of time. So first, let's do, and we're going to do some different examples. So I'll just call this first one y1 and do the cosine of time. And the way this works is just like you would do for a scalar, you can pass that argument into the cosine function. Now MATLAB functions are well equipped to handle vectors. So what will happen when we do this command is it will take the values of time and evaluate the cosine at every component in that vector. So if we wanted to run this, and I'll leave my semicolon off, if we leave the semicolon off, that will actually output the result of that calculation. Go to my editor tab and then hit run. And the first time I go to run, I'm going to need to save this file, and I'm just going to go with a poor file name and call this MATLAB demo 2. So I run that. Now I see my result here, my y1 is a 1 by 1001 row vector, and that's the same as my time. So I gave it 1001 values to calculate the cosine, and then it did that. And it's putting on the screen here all these values. Well, that's not particularly useful for me at this time, but let me go through a few more examples and then we'll come back to that. So what happens is, what if I try to do t squared? So I want to evaluate the time squared. And if I try to run this, I'm going to get an error. And what this error says is that it's an error using this caret, the exponent operator there. And it's talking about this being a square matrix. It's talking about matrix stuff, but we have a vector here. Now what happens is MATLAB defaults with certain operations, and it is this caret operator, multiplication, and division, and each of these are going to default to matrix operations. But that doesn't mean that we can't do things with a vector, but because what's happening here is what it's trying to do when you do t squared is it's trying to do essentially time times time. So that's a 1 by 1001 times a 1 by 1001, and it's trying to use matrix multiplication to do that, and it can't because the inner dimensions do not agree. So the way to handle this in MATLAB is, well, all we want it to do is take each component of that vector and square those individual components. So rather than do it as matrix multiplication, we want to do what's called element by element operations. And the way MATLAB does that is using a period or a dot before the operator in question. So if we make this t dot caret 2, run that, we'll get rid of that error. And we now see that we've calculated a y2 value, which is also a row vector now. So let's do something crazy. We've got, and first I'm just going to type it in roughly, and then we'll go back and fix it. T times e to the t, so exp is how MATLAB does exponential, divided by cosine of t over 100, plus 1 divided by t cosine t, plus t over 3. So if I just type this in there again, if I try to run this, I'm going to get these errors. I'm going to get this inner matrix dimension error because it's trying to matrix multiply things that we don't want to be matrix multiplication. We just want the first element times the first element, the second element times the second element. So let's go through this and see where that needs to happen. So starting right at the beginning, we've got t times e to the t. These are both vectors, so when I go to multiply these two, I'm going to have a problem. So I need to put a dot here. So this whole numerator part, that's now a vector, and this denominator is also going to be a vector, cosine of t. There's a t in there, so that'll be a vector. So when we go to divide here, we also need to add our dot. Now inside the cosine, we have this t divided by 100, and we might think because we have that time value there and that's a vector that we need a dot before this division sign, and we actually don't, because there we're just taking a vector divided by a scalar. That 100 is a scalar, so it will be able to do that division as a scalar division. So it just takes every component of the vector divided by 1000, so you don't need the dot there. Moving forward, we've got 1 divided by, and then, so t cosine t, vector times cosine of a vector, we'll need the dot there. But the other thing here is that 1 divided by a vector, that's not the same thing as the we had for here with the t divided by 100, because that's a vector divided by a scalar, whereas this is a scalar divided by a vector, and dividing by a vector is not something that you can just do. You're going to need that dot there. The last piece, t over 3, this one, just like the t over 100, is okay. We don't need the dot there. I'll put my semicolon on here because I don't want to see that result. But if I run that, no error. So now I'd like to talk a little bit about plotting. So I'm going to stick with that same time vector, and I'm going to do a couple plots. So I'm going to say, let's do some plotting examples. So first thing I'm going to do is I'm going to look at a function, and I guess I'll just keep incrementing my values, which these are not great variable names, by the way. But I'll do y4 equals e to the t. And then I will generate a figure. So I'll call that figure 1. And then I'm going to plot t and y2. So that figure command will open up a figure window. And then the plot command is going to plot a line on that. The default for plot is to create a line. And so if I run this, what we'll see is that we get this figure window, so figure 1 pops up, and we get this line, which is the plot of t and e to the t. So what we see here, we don't have labels on here yet, but this x-axis is our time, and then this y-axis here is the y values, that e to the t. So if we wanted to label this figure, make it look nice, which you want to do in general, you use the xlabel command to add an x label to your figure. So we could do this however we want. We could say time in seconds, or you could use t, or whatever you want. And when I do that, we'll just do these one at a time. If I run that, this will show up here on the figure, and this will tell me what is on that axis, and it's also really good practice to include your units on there. We can do the same thing for the y-axis, so you use y label, just like x label, and in this case, we have that function y, so maybe we'll write it this way. We'll say y equals e, and we could do this. If we do that caret in a label like this, it will actually make that a superscript. So this will look kind of nice. We'll do that, and I'm going to do one more thing because it makes figures look really nice. I'm going to type grid on, and what that will do is that'll turn on the major grid lines for the figure. So let's run this and take a look. So here we have our time. Here I showed that what we're plotting is y equals e to the t. Then we have on our figure now, these lines are our grid lines. That's from that grid on statement. So we notice on this plot here, this might not be the most useful line to look at. This figure is, this exponentials, we're not getting a good idea of what's going on here. The default of a plot is just to plot those x and y values as is. But that doesn't mean that we can't change our scale, and there's an automated way to do this. So let's do a new figure, figure 2, and instead of typing plot, I'm going to look at semi-log y. The semi-log is saying that I'm going to do a log scale for half of the axes, so that's the semi part, just on the y. So semi-log y will do a log scale on the y-axis. And so if I do the same thing, and I'll even go ahead and copy and paste these because these are still valid. If I run that, now I get my new figure. I still have my figure 1. I didn't get rid of that. I have this new figure, and now this is on a log scale on the y-axis. And so this is nice. Since this was exponential data, when we do the log scale, this looks like a line. But we have on here the real values of that function, and here we have time. So these are different ways of plotting the same data. So let's get rid of these. Let's do a new example now. So I'm going to use that same time vector, but now I'm going to look at a new y, and I'll just keep incrementing here as we go through these examples. Sine of t to the 1/7 power. Now when I go to do this, I'm going to need that dot before my caret. So let's create a figure now, figure 3. I'll start with a plot of time y5. Let's copy these labels here, except now we've got sine of t to the 1, and here's a little trick. If you want a bunch of things in a superscript, you just need a caret before each item. We'll see if that works. 2, 3. Okay, so we've got sine of t to the 1/7 power. That did work. And we're getting something that looks like this. So this again, so the plot is just giving us the data as is, plotting on both linear scales. This is again a case where if we really cared what was going on here around 0, we're not getting a good picture of that. So in this case, it makes sense to look at a figure. So we'll make a new figure. Plot t, or sorry, not plot. And this time we're going to do semi-log x. So we can do a log scale on the x-axis. These lines are still valid. And let's run that. So now, in this case, it's not perfectly aligned, but what's happening is we're getting a much better image of what's going on with this data. So if you start, and usually it's good to just start with the plot command, but once you do that plot, if it's not looking right, or you want to get a better view of what's going on, just realize that these log scales are available. So let's round this out with one last example. Let's look at y6 equals t squared. So when I go to do t squared, I need my dot caret, and I need to dot multiply times e to the t. And then here, let's plot t y6 just to take a look. You always want your figures labeled, make them look nice, so take the extra time to do this. Let's write this, so t squared e to the t, run that. So now we're looking at something here, and this is also kind of significantly skewed in how we're looking at this. We don't have a good idea of what's going on down here. We're also very heavily shifted on both scales down to this corner. So let's do the last type of scaling that I want to discuss. I forgot to create a new figure here. If you don't use these figure commands to create a new figure, you can either explicitly put 5, or for this last one I'll do it different and just say figure. Figure will open a new figure. If you say figure 5, it will always plot on figure 5, which will sometimes overwrite what was there before. But if you just do figure, it'll just increment and add whatever newest figure it can open. And I did it again. I don't want to plot. This time I'm going to do log log. And when you do log log, that will plot both axes on a log scale, so x and y. So let's run this. So this is still giving me figure 6, even though I didn't say make it figure 6. It just opens up the next window. But what happens is, and I'll show this to you first, if I run this again, now I have a figure 7 because it didn't overwrite the figure 6 that was there before. So I get this new figure 7 opening up. So in general, you usually want to explicitly tell it what figure you want to plot on. Otherwise, you end up with extra figures hanging out. And if we do this here, again, we get a nice image of what's going on with this function. So when in doubt, try these different options until you get things looking the way that makes sense to display your data set. So these examples, we've all been doing plotting one line on one figure, but we don't necessarily have to do that. I'm going to go back and make this that 6. So let's go, and for figure 7, I'm going to do something different. I'm going to use what's called the subplot command. And when you're doing subplot, what you need to do is you need to define a grid of where you want graphs to go on your figure. So for example, I could do 3, 1, and that'll be a column of 3 figures, or column of 3 graph windows all in one figure. And then the third command is which one I'm going to plot. So I'll start with the first one, and then let's just say I'm going to plot t and y4. And then for that plot, we can have its own labels. So y4 was this e to the t. And so if we do this, well, let's just run this. If we do that, we get figure 7, and it's plotting, it's creating 3 spots for graphs, but we've only put 1 in there so far. So if we want to add more, we need to complete it. So it's still 3, 1. We're still on the same 3 by 1 grid, but now I want to do the second plot. And let me just go up here and grab this thing we were plotting before. So this is the y5, and this one, it can be plotted on a semi-log scale. There's no reason why we can't plot them on different scales. And just to speed things up a bit, I'm going to do that third one as well. I'll grab the log and run that. And now, so what we get, and I'll go ahead and make this bigger, we can get 3 lines of data all in one figure window. And sometimes this is nice because you can look at things nicely together for comparison or whatever. So that's available. You can also do, and let me just go in here and tweak this. If you just change, instead of going 3 by 1, you go 1 by 3, 1 by 3, 1 by 3. If you do this, you'll get this same result, but now you're plotting these things across a row instead of a column. So you have that option, and you also don't need to do just a single row or column. You could do 2 by 2, 2 by 2, and then we could actually have room for a fourth, but we don't need to necessarily do that. But if you wanted 4 figures, you could plot them all in a square like this. And you can do any number of rows and columns and put this together however you like. So that's the subplot command. So that's how you can plot different lines on different graphs within the same figure. But we can also do this, let me go figure 8 here. We can also do this on one graph. Now I'm going to create new lines for this one and say, we'll do, well, we did already have this variable, but I'll just redefine it. y8 as t over 10. So these 2 lines, and I want to plot them together on the same figure, same window. And how we can do this, there's 2 ways. So I'll do it the first way first. So time y7, and then I can just write in one line, put another pair of data in there in my plot. So I can plot them both just like that, and then well, let's just look at that. So what it will do is it'll put both of these lines on here. Now I don't have labels or grids or anything on here yet, but I can do that. The other piece then, now we've got 2 lines on this figure, and we don't really have a great way to say which one's which yet, because if we just put a Y label here, we don't know which figure we're talking about. So that could be, this here is what you want to describe something that's relevant to both of those lines. But how you want to distinguish those 2 lines is by using a legend. And the way to create a legend is by using the word legend, and then in single quotes you write the string of what you want to refer to. So in this case, this not very great example, I could do y7 and y8, but typically you want to label what those things are, like position, velocity, or whatever this is in reference to. The way I put these in here, if I put this up, these will appear, and those underscores, just like how we did the caret before, the underscores will give us subscripts. So that's another nice little tip. So that legend will appear there then. And you can do your X labels and grids just like before. I won't do that just for time purposes. Let's do the other way. So using those same values, I can do plot t y7, and then I don't have to do it all in one, but what I will need to do is, if I have my plot command, that'll plot the first line, but you can use this command, hold on, and that's basically telling the figure to wait because you want to put another data set on there. And then you can plot t y8. Now what happens if we do this, I run this, we'll get both those lines in there, but they're both defaulting as blue lines. So what you want to do is you want to tell it how you want these lines to plot, and you don't have to stick with the defaults. If for this first one, rather than plotting as a blue line, I could make it a red line, and if I just put that, it'll just make that line red. And for here, I could, let's say, make it green, and these are shortcuts that you can look up in MATLAB for different colors. And I could make this one a dashed line. Dash dash will make a dashed line. So if I do that, I get a red curve there and a dashed line here. Now, one thing with the hold on command is, if you keep that hold on there, you'll see that blue line that I plotted before is still there. So I have the blue line and the dashed green line on there. So what you'll want to do is add a hold off statement at the end. And that way, as we run that, so this is still open from before. Let me close that and run that. There we go. So now that will just plot what we want, and then it knows to, when you do the hold off, it knows to stop putting things on that figure. So there are also some other things you can change. Maybe you wanted that green line to be thicker. You can use the line width command. So just at the end of your plot, type the string line width, and then you can set it to whatever you want. Let's say 3. The default is 1, so that will make things thicker. Rather than dashed, you can do dash dot. There's also colon. We'll do a dotted line. So let's take a look at those. So I made here a thicker dotted line. Here I did a dash dot line. The other thing that you can do is you can plot things with or without markers. So you could do this as red circles. And we have a lot of data points here, but if I zoom in here, we can see that it's just taking those data points and putting them in as circles. So these are some of the options that you have. The last thing I want to talk about is, so we've got these vectors, and sometimes we want to look at different relevant statistics with these vectors. So let's pick, for example, the y5 vector. And MATLAB has some functions that will tell us some interesting stuff about that. So if I want the max of y5, I can type that in here, and that will give me the maximum value of that function. We can also do the minimum. The smallest value of that happens to be 0. We can also calculate the average or the mean average, and that will give me the mean value of the components in that vector. We could also do median, for example. So there are all sorts of vector functions that we can use to calculate different things of interest. So that was my introduction to vectors and plotting, and that's it for now. Thank you.